All right, General Chemistry 2 class, here we go. This is the video for March 31, the last day of March in 2021. As far as the announcements go, here are the ALEKS due dates for Chapter 18. For Chapter 18, we're actually probably just a little bit ahead of the game in terms of the lecture material. So for 18A, it's due tomorrow. That is basically all of the buffer stuff, the acid-base titrations. So hopefully you've had enough time to work on that. After tomorrow, over Easter break, because, hey, nothing says Easter break more than working on ALEKS. We've got some open pie for 3 days here. And then Chapter 18B is due next week. It'll be due a week from tomorrow, a week from Thursday. So we'll have class today, and then we have this break, and then class next Wednesday. So we have a week in between lectures. So the lab that you're in the middle of this week, some of you have had it, some of you will have it tomorrow, is buffers. Worksheet 18 is due tomorrow night. It's due the 1st. For those of you who are on the online class, worksheet 18 is due. We'll cover all of this material today. And then for worksheet 19, that will be due next Wednesday night, a week from today, for the upload. So keep that in mind for the online class especially. And then exam 3, of course, is coming up in a little over 2 weeks. Something to look forward to. We always have to have these exciting milestones in our headlights here. And of course, we have a little bit of despair today. Let's see, and let me see if I can turn down the lights just a moment. Maybe make it a little bit clearer. It's a nice bright day here today. It takes a lot less time, and most people won't notice the difference until it's too late. Just because we accept you as you are doesn't mean we've abandoned hope you'll improve. Everyone loves penguins. None of us is as dumb as all of us. Teach every child you meet the importance of forgiveness. It's our only hope of surviving their wrath once they realize how badly we've screwed things up for them. A job worth doing is worth doing right, over the shoulder by your boss. While good fortune often eludes you, this kind never misses. And finally, oh, this is harsh. It could be that the purpose of your life is only to serve as a warning to others. Ouch. All right. Solubility equilibria. So we're going to continue talking about sparingly soluble compounds. Sparingly soluble compounds, this whole idea of solubility equilibria. So we talked in our last video, we ended the last video about the solubility of lead iodide in water. So we're going to walk through the slides at the end. And this is the common question. What is molar? Remember that we have two aspects of solubility that are quantitative here. We have the solubility product, that's your KSP, it's the equilibrium constant expression, and the value of KSP. And then we have molar solubility. Molar solubility is the molarity of the insoluble or sparingly soluble salt that dissolves. Write the reaction to the ice table, sulfur X. X is always molar solubility. And so we talked about this. I hope this is coming out okay on the video. Sometimes these colors, trying to make things look a little more lively, doesn't always show up great. Now let me see if I can just do this without that particular light. Okay. Every salt equilibrium reaction is written the same way. Salt on the left goes to cation plus anion. It is always the same pattern. This is always a two-component equilibrium constant expression. KSP is equal to the cation concentration times the anion concentration raised coefficients become the exponents. Make sure you're careful about the stoichiometry, which occurs in the C part of the ice equation, or the ice table. And then make sure that this comes through at the end, x and 2x. When you put them into the equilibrium constant expression, again, remember that it is 2x, the whole thing squared. It is not just 2x squared. It becomes 4x squared times x to give 4x cubed. On your calculators, and by the way, I'm not sure this is correct. Let me do this calculation just to be sure. Let's see. Calculator, here we go. Nope. Do not want settings. That's right next to calculator. Here we go. Okay, I'll get there. Don't worry about it. You can always fast forward. I'm sure most of you fast forward anyway, which I would do if I were in your shoes. Let's see. 1.4 times 10 to the minus 8th. Nope, not happening that one. Okay. Let's see. 1.4. Here we go. Times 10 to the minus 8th. So I want to divide that by 4, which I get 3.5 times 10 to the minus 3.5 times 10 to the minus 9. And now what I want to do is take the cubed root of that. And that is not this number. I don't know where this number comes from. So I apologize for that. It is not 0.00383. It is 0.00152. So let me just go ahead and change that right now. Let me just go ahead and change that right now. 152. Okay. And then this is 1.5. All right. I apologize for that. Now let's see. Let's go back and let's go to the window and share this. There we go. Okay. I think I've got these numbers right now. 0.00152. Yeah, this is one way that we can extend our video time. So you're getting your money's worth, right? Okay. Now we're going to do something a little bit different. A little bit different. We're going to take the same equilibrium, the PBI2 equilibrium. And now the question is, what is the molar solubility of this, not in pure water, but in a solution that already has some lead ion in it? You already know that lead nitrate is soluble. So if you see PbNO3 taken twice, you know that in solution as a strong electrolyte, as something that's soluble, it totally separates into Pb2 plus and into nitrates. Write the reaction, complete an ice table, solve for X. Same process the whole time. So this is how, the only way it's different. The only way it's different, we use the same reaction, except now already in solution is some Pb2 plus. It is 0.100 molar in lead nitrate. So if it's 0.1 molar in lead ion, that's what we're starting with. You don't have any iodide. Any iodide is going to come from PbI2 dissociating. So that forms 0.1, 0. The change always goes left to right. Unlike some of the acid-base equilibria, which can go right to left, or other equilibria, solubility product equilibria always goes from left to right. So we're forming X and 2X, just like before. The change is exactly the same as what it was, same as it was when we were dissolving PbI2 in pure water. At equilibrium, we now have a different set of equilibrium values. We already have some lead that is in the solution. Same equilibrium constant expression and same K value. We plug in the values. ASP, the concentration of Pb2 plus. This is why it's important to write the ice table. You take exactly, now for these especially, because it can get messy. You take exactly what you got is the equilibrium concentration of Pb. In other words, this is the equilibrium concentration of lead at equilibrium. This is the equilibrium concentration of iodide at equilibrium. So we plug this in, 0.100 plus x, and that becomes 2x. Remember, the whole 2x is squared. So we get 4x squared. We're going to make an assumption here. You always, always, always make this assumption. You go back later to make sure it's correct, but you always ignore the x that is added to or subtracted from another number. In this case, it'll be added to insolubility equilibrium. So this just simplifies to 0.1. Let's go back. Why can we ignore this x? Let's go back to the previous problem. X had a value of 0.001 or 0.0015. Is 0.0015 going to change this number? 0.0015. It might change it a little bit, maybe 1%. Does it matter? Maybe, maybe not. But we'll ignore it, solve for x from this term, and see if it's a safe assumption. All right, so if we ignore the x, this just becomes 0.1. 2x, the whole thing squared becomes 4x squared. KSP is equal to this times 4x squared, which is equal to 0.1 times 4 is 0.4, x squared. So we solve for x squared and then solve for x. Now, because I don't trust my math, and you shouldn't either, let's try this again. So 1.4 times 10 to the minus 8th divided by 0.4. And now, this time, it's just the square root. And I get 0.000187. So this is correct. I did this calculation correct. How about that? Still have it. Okay, 1.87 times 10 to the minus 4th. We'll round it to 1.9 times 10 to the minus 4th. So the molar solubility for lead iodide in a solution that already contains a little bit of lead is lower than if it were just going into pure water. We'll come back to that concept in a minute. Take your time, work through these calculations, do them yourselves. Now let's do another problem. Let's do one more problem. Solubility, again, lead iodide again. What if instead of dissolving it in a solution of lead nitrate, remember, the lead nitrate, is this right? Oh, this is just answering it. So the molar solubility, okay, was it, oh, sorry, let's go back. Was it valid to ignore x? Was it valid to ignore x? We ignored x. X is 1.9 times 10 to the minus 4th. 2 times 10 to the minus 4th, 0.0002. 0.0002. Is it okay to ignore x? Absolutely. That 0.002 is not going to make any difference there at all. Okay, so the molar solubility of PbI2 in lead nitrate is 1.9 times 10 to the minus 4th. Let's do one more problem with this. Instead of dissolving PbI2 in water or in a solution that already contains lead 2 plus, what if we have a solution that already contains some iodide, some sodium iodide, NaI? Because sometimes it's hard to get our minds around this. This happens in lab all the time, where students will say, like in the iron thiocyanate lab, you remember that, the Beer's Law plot. It was where we calculated the Kf value for iron thiocyanate 2 plus. I'm sure you do, of course, plain as day. In that particular lab, where was I going with this? Oh, the instructions will say, go get some, you want to make so much thiocyanate. You want to get thiocyanate ion and add it. But the bottle says sodium thiocyanate. And students will say, where is the thiocyanate? It's like, that's what it is. Don't be confused by the sodium, because by now you should know that NaI, soluble, strong electrolyte, if this is 1 molar in NaI, that means that it is 0.1 molar in sodium ion and 0.1 molar in iodide. We don't care about the sodium. The sodium just gets the iodide to the concentration that's desired. Everything else then is the same as we approach this problem. The initial concentration of iodide is 0.1 molar. So write the reaction. Here's the ice table. How are things different? Instead of 0 and 0, instead of 0.1 and 0, now we're told that our initial concentration of iodide is 0.1. So this is our initial set of values. Again, we go right to the exact same amount, to the x and plus 2x. At equilibrium, this is what we have. The x represents the concentration of lead 2 plus. 0.1 plus 2x represents the concentration of I minus at equilibrium. We plug this in for lead, we plug this in for iodide, and that whole thing, everything here that you see, is going to become squared, like this. So we have our KSP value. X is the lead 2 plus concentration. This is the iodide concentration. We have an X added to another number. Always ignore that X, always, and then go back and see if it matters. So if we ignore X, this equation simplifies to X times 0.1 squared. Don't forget the squared. Don't forget the squared. Which is equal to 0.01 X. 0.1 times 0.1 is 0.01 times X. In order to solve for X, we don't even have to do the calculation here. Just divide both sides by 0.01. X is 1.4 times 10 to the minus 6th. Does this number, does X matter when it's added to 0.1? Think about it. No. So this is on the order of 3 times 10 to the minus 6. 10 to the minus 6 is way over here. It's way beyond 10 to the minus the third decimal point there. So ignoring X will nearly always work. Notice that this value, however, is different from the molar solubility from the X values that we got for PbI2 in pure water, or for PbI2 dissolving in a solution that already contains some lead cation. So is it valid to ignore the 2X? Yes. What we've just talked about is the common ion effect. It's the common ion effect. If we have a solution where we already have some lead, this can't go as far to the right as it normally would want to. If instead we have a solution that already contains some iodide, this equilibrium cannot go as far to the right as it normally would want to. With nothing here already, if we're just putting this into pure water, then we get the molar solubility of this in pure water with nothing already there to help prevent this going. Think of it, now let's think of it another way. Let's do this little thought experiment. Let's say we have PbI2 dissolved, and it's now in equilibrium with lead and iodide. We have this nice equilibrium set up. What happens if we add some PbI2? If we add some of that, it's going to shift the equilibrium to the left and use up some of this. If instead we add some iodide to a system that's already at equilibrium, it's going to shift it to the left as well. Le Chatelier's principle, basic equilibrium from chapter 14. So having a common ion limits, it doesn't shift the reaction won't shift to the right as far as it would normally want to. All right, so this is not 3.8. What was that number again? Let me go back to There we go, 0.00152. .00152. So this is going to be yep, this is what happens when I don't do my calculations correctly. Let's see, make that go. Let's go back to sharing the window. All right, here we go. So these are the numbers. This is the molar solubility in pure water. Notice that this number, the solubility, the ability for the salt to dissolve more is decreased, here by about a factor of 10. From here to here, it's by a factor of 1,000. So the stoichiometry makes a difference, because remember that the iodide was a squared term in the equilibrium constant expression. Bottom line, molar solubility decreases when you already have a common ion there. All right, how are we doing with all this? Any questions? Any questions on that? I'm not hearing any. Probably because there's no one in the room. All right, let's move on. What happens now when we dissolve magnesium hydroxide in water? Is this soluble or insoluble? You got it, it's insoluble. It's insoluble because hydroxides are generally insoluble. Mg is not one of the magic cations where everything is soluble. What is the pH of a saturated solution in water? Now we can address a question like this. Let's go ahead and figure this out. Same process as we've used before. Write the reaction. Magnesium hydroxide on the left, cation and anion on the right. Initially, there's nothing. Do we truly have zero hydroxide? Well, in pure water, it'll be 1 times 10 to the minus 7th. 1 times 10 to the minus 7th is practically 0, so we'll just say 0. The reaction shifts to the right, x and 2x. We have our equilibrium. This is just like the lead iodide stoichiometry. Look familiar? Coefficient of 1, coefficient of 2. And then we plug those x and 2x into our equilibrium constant expression. We look up the value of the KSP, or it will be given to you. There are tables in your book, which you should memorize, because memorizing KSP values matters. Okay, no, it doesn't. You can look them up, they'll be given to you. You don't have to know them. But you need to know how to use them. So for magnesium hydroxide, KSP is equal to x times 2x, the quantity squared, or x cubed. All right, I'm going to do this because I don't trust my math from before. So this is 1.2 times 10 to the minus 11th. And that'll be divided by 4. And then the cubed root of that number. 0.000144. 1.44 times 10 to the minus 4. Okay, that is correct. Perfect. X represents the molar solubility of magnesium hydroxide in pure water. This is the same process we've gone through before, and hopefully this isn't too challenging. This is a fairly straightforward idea here. So at equilibrium, however, the hydroxide concentration is 2x, because we form for every mole of magnesium hydroxide, we have 1 mole of magnesium ion and 2 moles of hydroxide. So the equilibrium concentration is 2x. So we multiply x times 2, 2.88 times 10 to the minus 4. Now that we know the hydroxide concentration, we know the pH, because you have done this 1,000,000, 1,000, 100, maybe at least 10 times. You've done a calculation where you've converted hydroxide concentration into pH. So the pOH, the negative log of this number is 3.54. The pH is 10.46. Try this at home. Try this on your own. Hopefully you get the same numbers. So how are we doing so far? I'll take that as you're doing great. Let's take another little twist on this. What do you do with molar solubility if we have something like magnesium hydroxide and pH 12 buffer? And pH 12 buffer. What this means is this. It means that we are fixing the hydroxide concentration at pH 12. Now, is pH 12, does that give us hydroxide concentration? Kind of, not directly. We have to go from pH to pOH to hydroxide concentration, but that will fix that number. And here's how that plays out in a calculation. Or does it? Okay. Yes, it does. So here's the deal. So if the pH is 12, the initial hydroxide concentration is 0.01 molar. We want to know the initial hydroxide concentration, and that's what we have. This is just like starting with 0.1 molar lead 2 plus, 0.1 molar iodide minus for the lead iodide example. Now what we're doing is we're saying, this is the hydroxide concentration at the beginning. The equilibrium goes from left to right. We form X molar magnesium and 0.01 plus 2X, remember the 2X, hydroxide. And we plug those equilibrium concentrations into the KSP expression. 1.2 times 10 to the minus 11th, X, 0.01 plus 2X, that whole thing squared. We ignore this X. So this becomes X times 0.01 squared. 0.01 squared is 1 times 10 to the minus 4th. 1 times 10 to the minus 2 squared is 1 times 10 to the minus 4th. And so that's where we get this. We don't even have to do the calculation. X is equal to, because this just is a nice clean number. X is 1.2 times 10 to the minus 7. In other words, we can find the molar solubility if we have a common ion. This is called the common ion effect. Here we already have hydroxide in solution. How soluble is this compound in a solution that already has that, some of that dissolved? Was it safe to ignore X? X is 10 to the minus 7th. 10 to the minus 7th times 10 compared to 10 to the minus 2? No contest. We can ignore X. That is safe. All right. Let's take a pause, take a breath, stand up, shake your head out. And we're going to do one more example. And then this is going to be it for chapter 18. This is the very last piece of chapter 18, and we'll talk about that now. Let's look at something that's a little bit more complicated. Let's look at calcium phosphate. What is the solubility of calcium phosphate in water? First of all, is calcium phosphate soluble or insoluble? Well, by now you know your solubility rules, and you know that phosphate compounds are insoluble. Calcium phosphate is insoluble. By the way, before I go any further, I just want to make one more comment here related to this, and that is a derivative of this compound is the primary structure in bones. So the calcium that's in bones is in the form of a mineral of calcium phosphate. If there is a hydroxide in here, if you have calcium 5, bear with me, calcium 5, that's 10 plus, 5 times plus 2, 5 calcium, Ca5, PO4, 3, that's minus 9. Calcium's plus 10 total, phosphate's minus 9 total if we have 3 of them. That last anion, so we have plus 10, minus 9 from phosphate. We need one more minus 1 anion. If it is hydroxide, that is a mineral called hydroxyapatite. And hydroxyapatite is the primary mineral in bones. In teeth, that's what teeth, the primary bone structure of teeth, hydroxyapatite, Ca5, PO4 OH. What happens with tooth decay is that the acids in the mouth from bacteria, from breaking down food, just the general stuff that's in the mouth is acidic. And those acids, especially, not always acidic, but if we eat a lot or drink a lot of acidic things, so for example, if we drink a lot of soda pop, we've already talked about the pH of Coke or Diet Coke or Pepsi or cola products. The pH is around 3.5, maybe 4, very acidic. The acidic nature of Coke, Diet Coke, pop, can break down, can react with the hydroxide of hydroxyapatite, the Ca5PO43 OH. That hydroxide can be worn away. The bone structure can erode, and that's where we get cavities. So drink a lot of soda pop and keep your local dentist in business. What happened, and this is also true if you eat acidic foods with a lot of sugar, like if you eat candy a lot, sugary things. Sugars will get converted by bacteria in the mouth to carboxylic acids. And those carboxylic acids from the breakdown of sugars will also attack teeth. So it's not just soda pop, it's also acidic foods. In water supplies, they add about a part per million of fluoride ion to water supplies. And what happens is, and this has been going on for 50, 60, 70 years. They actually did studies and found that if they put a trace amount of fluoride in water, that fluoride can, on occasion, not very often, but on occasion, fluoride can replace the hydroxide of hydroxyapatite. So now what you have is a fluorapatite, Ca5, PO4 taken 3 times, F. You don't want very much of it, but a little bit of fluoride goes a long way in preventing tooth decay. This is why fluoride is added to water. All right, didn't mean to get off on that story, but sometimes I can't help myself. You don't want too much fluoride. Too much fluoride will turn your teeth black. And so that's not necessarily something that people want. So let's do the molar solubility of calcium phosphate. Now we're back to just plain calcium phosphate in water. What is the molar solubility of calcium phosphate in water? Right reaction. Salt on the left, cation, anion. This time, coefficient is 3, coefficient is 2. So at equilibrium, we have these numbers. The KSP expression. The KSP expression has calcium cubed, phosphate squared because of their coefficients. Don't get confused. Be systematic with your ice table. And then from these equilibrium concentrations fit into those concentrations. So let's take a look. Here's the KSP, 1.2 times 10 to the minus 26. But then you've already memorized that. Good job. Here is the calcium ion concentration, 3x at equilibrium. That's cubed. 2x for phosphate, that's squared. This is where you need to be careful. 3 cubed is 27, not 9. 3 squared is 9. 3 cubed is 27. X is cubed. You cube your numerical value and you cube your variable. Where we square the numerical value and we square the variable. 27x cubed times 4x squared, which gives us 4 times 27 is 108, x to the 5th. Now we just solve for x. Piece of cake, right? Actually, it's not bad. Divide both sides by 108. We get this. And now we take the 5th root of x. So on my phone, I have square root and I have cubed root. I also have a squared button and a cubed button. On your calculators, I'm hoping that you have those buttons as well. But how do we do a 5th root? It's the same as saying we take this whole number raised to the 1/5, raised to the 1/5, raised to the 1/5, raised to the 0.20. If we raise this, x to the 5, if we raise that to the 1/5, it becomes x. If we raise this to the 1/5, it becomes this number. And this number is the molar solubility, 2.6 times 10 to the -6. So we have the molar solubility of calcium phosphate in pure water, but X is not equal to any of the ion concentrations because calcium ion concentration is 3x, phosphate is 2x. So if we want to find those concentrations separately, their equilibrium concentrations, we have to multiply by those respective values. Molar solubility is the molarity of the salt that dissolves. Solubility product is KSP, and it's represented by the KSP expression. Okay, so this is just a summary of the last 3 problems that we've done, and we're going to stop there. I hope everyone has a good Easter break, and we'll talk to you next Wednesday.